So, did you need to use a thicker PCB than standard?
No, it was basically the cheapest.
Basically the cheapest.
Yeah. That, yeah, cost was a driving consideration in this one. Yeah, yeah, it's true.
How did you not choose to use a Bendy PCB?
Luck.
Well, no, we wanted it to be bendy, actually, didn't we? We wanted a little bit of flex and suspension. Like, if that was possible, that would have been a good thing. And like fiberglass of PCBs is a good structural material for a chassis. So,
in fact, it turned out not to be quite as bendy as we'd hoped for, because we thought that when the robot was loaded, we'd ensure that we would always have, maximum kind of contact with the ground with the wheels, that the chassis would actually kind of flex and bend. But actually, it turned out to be surprisingly stiff. So we actually had more problems with traction than we thought we would. It turned out we would have kind of 3 or 4 wheels on the ground, even on the flat. So actually, we could have done with it being ever so slightly flexier.
What's the ground clearance like?
It's like 35 millimeters, 40 millimeters.
Yeah.
It's a little bit better than a tiny chassis. Like, we did everything fine a couple of years ago with a tiny chassis. So the motors, they're standard N20 motors, just offset from the chassis just slightly.
Okay. How well does it handle undulating surfaces and obstacles?
Very well.
Oh, well, really? Yeah.
Let me get the chassis.
So the keen-eyed amongst you will have noticed that the wheels are in a slightly unusual arrangement, in that the one in the middle is offset.
Show it.
The idea was that being 6-wheeled, even when it was going over obstacles or up inclines, you'd always have 4 wheels touching the ground. So you'd have good contact as it was kind of tipping forwards and backwards, as my assistant will now demonstrate.
Yeah, so we've got the front and rear bumpers protect our sensors, and there's kind of a bit of a bash plate on them, so we can go up and down 45-degree slopes fairly well. It only goes onto 4 wheels when it does that, but it's
Cool.
fine.
Mark, apparently there's beeping coming from your side or something. It's going back. Beep, 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 beep. You got 3D printer running or something?
Okay. I'll turn my speakers down.
No, it's not that. I just wondered what it was. Anyway, never mind. We'll crack on. What motors are you using? Gear ratios, that kind of thing?
So they're N20 gear motors, so the standard kind of small motors that you find in the tiny kit. They're Pimeroni 6-volt ones with the rear shaft sticking out the back, so we can put encoders on them. And then we overvolt them to 12 volts. So they're doing about 2,000 RPM. So they're pretty fast. They don't like stalling with that overvolting. We've had a couple die, but under normal autonomous conditions, they work really well.
How much does it weigh with the barrel holder and the attachment on?
I haven't weighed it, but the base chassis with the batteries and the motors and everything is about 700 grams. Fully loaded with the barrels and the whole attachment, it's more like 2 kilos. Like that attachment is really heavy.
Did you learn any lessons from Robot Wars that you applied to this?
Did we? I think generally we tend to continue designing all of our robots as though they're going into Robot Wars, and we're constantly having to say to ourselves, no, it's not going to actually have something to try to attack it whilst it's in the arena. So if anything, the thing we've learned is to be too cautious.
Arguably, we should have learned from our Robot Wars experience, because our Robot Wars robot is ridiculously complicated, and so is Tauradigm.
Is the robot unbalanced with the arm on and no barrels collected?
Yes, we'll probably have to add ballast.
Yeah.
What Raspberry Pi is inside it?
3B plus.
I think so. Yeah.
Yeah. Yeah. We really paid attention to that, but you can tell, can't you?
It's a question about alignment with the courses. How do you do north-south alignment with the courses? How does it know which ways are up and back, basically?
We're going to have to set that on the day.
Yeah. It'll just be a case of basically calibrating our north-south magnetometer readings to the north-southness of the courses.
Cool. What did you code it in?
Python mostly. Obviously, we use the Teensy microcontroller to do all of the high-frequency sensor reading stuff, and that's all in C. And then the two kind of communicate. So the Teensy is doing the kind of low-level stuff, and then being polled by the Pi. So the Pi side is all Python, and the Teensy side is all C.
And then we have another microcontroller on the barrel attachment, don't we, that runs C as well.
Yeah.
Question from GCC Pi Wars 2017. I think that might be... Oh no, I can't quite remember who that is. I should know. Have you tried your Monte Carlo localization in a real arena, and how long does it maintain its state for? Is there a time limit when it starts deteriorating?
Yeah, so it's a good question there. The animations we showed are based on real logging data. So whenever we drive the robot, we record all of the sensor values. We log everything. So we log the encoders, the accelerometer, the distance sensors, everything's logged. And then I've been feeding that through the algorithm. So what you've seen is Tauradigm driving in an arena, and it's where the library thinks we are. And you can see it tends to converge and stay with the robot. Once it's converged, it doesn't lose it again. So it seems like it'll work pretty well.
Yeah, it's kind of the opposite problem in that it takes, there's a little period of time at the beginning as it's actually homing in on its localization and actually deciding on where it is. And there can be a little period at the beginning where you've actually got kind of two areas where it thinks the robot could be, and then it takes a while to kind of settle down to be one. So it's sort of the opposite problem from having a lock and then losing it. It's actually acquiring that.
This is a good question from Lucas. What if there are more than 6 barrels per colour in the challenge?
We'd be
Excellent.
stuffed.
Question from Tanya.
Yeah.
Mark, do you have 2 cool workshops, or do you just have 2 camera angles?
Yeah, I have 2 almost identical workshops.
Another question from Tanya. Does it ever tip over with all the barrel collectors on?
When the arm's in the forward position and we've got one barrel at full reach and it's the first barrel, then it just falls over forwards. After that, it's fine. Tauradigm's quite wide.
So it's a question of making sure that it doesn't go out to full stretch on the first one.
Yeah, so what we do, we changed it slightly from just pick it up and pivot forward to twist to one side for the colour, to choose the colour, then go forward. So it just sticks out a little bit less, and that it doesn't fall over with that, well, you can see in the video. I didn't cheat that video, it did it okay, but we'll probably add ballast to...
How long does it take to load each barrel once you've found it? Okay.
I don't know.
No, it's pretty quick. I mean, the speed you see in the video is the speed it would be working at. Actually, I think in the video, I think it does the pivot and then the lift, whereas the latest version does the pivot and the lift at the same time. So it's possibly a second or two quicker.
Yeah.
How long would you estimate it would take to do 12 barrels, or does it depend where they are?
I don't know. I think we could probably do it in the time limit, but it could be quite tight. It's a lot of work to do.
Do you, when you're doing the warm up time for the Monte Carlo stuff, can you feed it some prior knowledge, or is it literally this course is this big?
If you know where you're starting from, then you can restrict the placement of the initial, I have no idea where I am particles. You can restrict those to a known bounded area, which means that you'll the chances of getting good hits from those particles is much improved. So you can really speed that up. If you're starting from an unknown position in a known map, it can take a while for it to kind of determine where you are. But if you say, well, I know the starting area is going to be in, a particular spot on that map, then you can restrict the initial spread of all those particles to just that, block, and maybe a little bleed around it, and then so that startup time is much reduced.
Did you use any simulations for this?
Yeah, a lot. So the Python, the Monte Carlo localization is basically a simulation at the moment. It's like we're feeding real data into it, but it's a simulation of the thing. We've simulated almost every other challenge as well. So I have a mathematical model of Minesweeper, so I know how fast we can go around and what our stopping distance is, so we can choose algorithms. We've chosen some of our algorithms before we've even started. The straight line speed was the same. We know reasonably well how fast we're going to do that and what course we're going to take. We've already programmed a course for that. The maze as well is the same. So we've found our robot is narrow enough that we can take the same course through the, I can't remember what it's called now exactly, the blind maze. We can take exactly the same course regardless of where the blocks are because we're narrow. So we've already got that course programmed because I've run it in simulation. But those simulations are incredibly simple kind of Excel models or Python scripts. Nothing kind of 3D or physics engine like.
Do you can it load the barrels while it's moving, or is it literally stop, pick it up, load it, move?
We could start moving once the barrel's off the ground.
Yeah.
There's a bit of a worry about it tipping up.
Is it all done on sensors, or is there a camera? I think I missed that bit.
No, we've decided not to use a camera this time because they're a nightmare.
Yeah. Having tried last time to do everything with only a camera, we decided this year that maybe we'd go with every single other type of other sensor we could get our hands on rather than a camera.
Are you planning on open sourcing it at the end? The code, I mean.
It's already on GitHub.
Can you put the link in the chat?
It's on my video is now public on YouTube, and the links are on there.
One last question then. What's the biggest improvement from Tauradigm? What worked better last time from the last autonomous robot you did?
The biggest improvement is probably multiple sensors, isn't it? Actually, the encoders is a big thing. Previously, knowing how much you turned and if you were moving was really difficult. Because if you've only got a camera, you just have to guess so much. Now we've got encoders, we can know we're moving slowly. And the magnetometer, we know which way we're heading, and that just makes things so much easier.
Yeah, I mean, I'd add to that the addition of a microcontroller for doing all of your sensor polling, and then communicating that stuff back to the Pi, and kind of splitting your concerns out into those, high and low frequency things. I think that's been a big improvement for us as well. Not trying to do everything in Python in one thing on the Pi, but trying to kind of have the Pi coordinate what everything else is doing on the robot, and actually having subsystems on the robot rather than just having everything on the
Cool.
Pi.
Well, I think that's come to the end of the questions, or at least the time we've got. Thanks so much for doing the talk and for giving up your time to answer the questions. Thanks, guys.
Thank you.
Thanks. Bye.
Okay, cheers.